Today I'm going to talk about titration. Titration is a lab technique that we use where you add a precise volume of a substance to another substance that you know the concentration of in a very precise volume. What it allows you to do is quantitatively determine how much of a chemical might be inside something, so how many moles, what its concentration might be, and it's a lot more accurate technique than just measuring in a beaker or something like that. So this is what we're going to look at. This is the general setup of what a titration might look like. This long piece of glassware here, it's got this thing called a stopcock at the end. This is a burette, okay? And the burette is typically where you're going to put one of your substances when you're doing your titration. So this is our burette. And inside our flask is the substance that we're going to titrate. We usually call this our analyte. So it's the thing that we're typically trying to find something out about. And the material in the burette is called the titrant. Okay, so just to remind you of a few key words, that material inside the burette is your titrant. And then you might see a little funnel. We use this when we're putting liquid into our burette. It's called a Burette Funnel. It's a much smaller funnel than normal ones that you're used to seeing. And the neck is really small so that it fits nicely in there and you have less of a chance of breaking the glassware using it. So this is our general setup. When you're back into the classroom, you're going to see how these can be used, and they're a very useful tool used all over the place. There's many different types of titrations. But for this particular course, we're going to focus mainly on what we call acid-base titrations. Okay, so we're going to look at acid-base titrations, and acid-base titrations deal with neutralization, right? So we're dealing with a neutralization reaction where you're going to see an acid and a base react. So our general equation, acid plus base, produces a salt and water, right? That's our general reaction that we're going to look at. So if we have an acid and it's in our burette and we put a base into our flask here, we can titrate that base with the acid. So we can add the acid in nice drop by drop to get the exact amount of acid needed to change the color of an indicator that we put in there. Okay, now the indicator itself changes color at what we call an end point. So once you see that color change, that's where we stop our titration. That's known as the end point. In a good titration, you want that color change to happen when you've added the perfect amount of acid to the base, right? The stoichiometric amount of acid to the base so that your reaction has reached that neutralization point, or more commonly known as our equivalence point when we're dealing with a titration. There's a few funny things. So as I said, we saw the word titrant. If you see the word teeter, sometimes you see this. Teeter is just the amount of chemical actually dispensed. So this is the actual chemical that's come out of the burette into the flask. That amount of liquid that gets used is called our teeter. And one other word that you might hear is the word aliquot. Aliquot is just the sample that we pipette. So typically what you'll see is to get a specific amount of solution in here, we might be using a base that's already in solution, so we're not dealing with any solid or anything like that. We're dealing with a liquid, so we'll use a pipette, a piece of glassware to get our sample. So an aliquot comes, if you think about it, you're going to have a container that holds what we call our stock solution. And our stock solution is like our original giant container. Let's say I've got 2 liters of stuff made up. I'm not using all 2 liters in my titration. I only want a small sample of it. So from my stock solution, I'm going to take an aliquot, okay? I'm going to take an aliquot, and it's going to go into, it's going to go into my flask. So I'm going to get a little small amount of it right in here. So my aliquot is that sample that I take from my stock solution and put in my flask. So just one other word you might see as you're reading or looking at material, that term aliquot. Now, the interesting thing when we're dealing with these particular burettes is that a burette, when you actually look at the burette itself, 0 is at the top. So when we fill this up, our 50 mark, and those are the type that we have at school, go up to 50 milliliters. 50 is right near the bottom. We fill it up to the 0 mark when we start our titration. And when we're doing a titration, we need to be able to read these volumes from your burette as precisely as possible. So when we are reading volumes, there's a few things we want to make sure we know from our burette. Okay, recognize that 0 starts at the top. So when I'm looking at it, if this is the 28 line, there's 28.1, 28.2, 28.3, and so on. So my numbers are actually getting higher as I go down, which kind of seems backwards to what we're used to seeing. But remember, it's about what we're adding. We started up here and we're adding some. So we're going down to this new volume. Burette readings on their own are not really useful. One single burette reading is not really what we want. We want to make sure we get an initial reading, a final reading, because then when we take the final and subtract the initial, that allows us to get the amount used, the amount titrated. Right, so it's the amount titrated is really what we want. So using that final volume and subtracting what our initial volume reading was, we can figure out the amount of that substance that was actually used, or the amount of titer that we had, right? Now, reading a burette, so if you're looking at it, as I said, this is 28, 28.1, 28.2, 28.3, 4, 5, 6, 7, 8. We always want to read, when we're dealing with liquids, to the bottom of the meniscus. So you're looking for where the bottom of that bump is. Right, the bottom of the bubble on the liquid. And I can see here that it's 28.8. It's between 28.8 and 28.9. It's somewhere in between here. So I'm going to do my best to estimate the second decimal place. So on my reading right here, I would say that this is 28.8. Everybody should agree that it's 28.8. But the next digit in any measuring device we estimate. So since we don't have any more markings now, we estimate. And I would say it's not really right at the 0.9 yet. It's a little bit lower. So I might say that's 28.87 milliliters, right? That would be my reading that I would take from this. So it's really important that you estimate that second decimal place. When you're dealing with a burette, okay? Very important piece when you're taking measurements using that. Always make sure any number that you record has 2 decimal places from these burettes that we're reading, because they are that precise. We can get to 2 decimal places. Okay? Now, as I said, the whole point of titration really, if we go back, is the whole point is to examine how one chemical reacts with another. And because we have specific volumes and we have concentrations, we can then determine what's happening with regards to moles. So if we know what the chemical reaction is, we can start looking at mole ratios between substances, right? It allows us to quantitatively analyze what's happening as precisely as possible. So let's try an example. Here we've got an example. Our first example deals with nitric acid. So it says a 10 ml aliquot of nitric acid was pipetted into a flask. 2 drops of phenolphthalein were added. So the phenolphthalein is just your indicator. Then the flask was titrated using 23.27 milliliters of 0.250 molar sodium hydroxide. And we're trying to figure out what the concentration is of nitric acid. So anytime we're dealing with this scenario, we go back to our same idea. We should really start with a balanced chemical equation, right? That's the first thing we want. is that balanced chemical equation. So if I look at this, I know it's nitric acid, and it's reacting with sodium hydroxide, which is NaOH. Both of those are solutions. And I'm going to create H2O because that's an acid, that's a base, so I'm always going to make water. And I'm going to make sodium nitrate. That's the salt that ends up being created. Right? And if I look, this equation, the way it's written, is already balanced. So there's no adjustment that needs to be made for balancing, so there's my balanced chemical equation. And then I start to look at what information I have. I know a volume of nitric acid. I know that the volume, I'm going to call it VA. A for acid is 10 milliliters. I know the volume of the base, so we'll call it VB, is 23.27 mils. I know the concentration of the base, 0.250 molar. Right? So I know that information, and there's enough information here in this question then that I can find moles of base. And once I have moles of base, I can use my molar ratio to figure out moles of acid. Right? And from that, I can look at what this question wants me to find, which is the concentration. Because if I have volume and I have moles, I can find the concentration. So my end goal is the concentration of this acid. So basically, this comes down to being a stoichiometry problem. The only way titration is involved in here is it's the lab technique that allows us to get the information that we need, right? So anytime we're dealing with a titration problem, it's just stoichiometry. The titration was the lab technique used to get that information. So from here on in, we just follow our same approach. We want to convert to moles, right? So that was our next step. So moles of base equals the concentration of the base times the volume of the base. So 0.250 moles per liter times the volume. And this we want to make sure we convert to liters. So 0.02327 liters. And when we do that calculation, our number of moles would be 0.0058175 moles. So that's our moles of base, right? Our next step then is to look at our ratio. Our ratio here, so the number of moles of acid to number of moles of base from our equation is 1 to 1, right? So therefore, number of moles of acid has to equal number of moles of base. So we know that value is going to be 0.0058175 moles, right? So once we've figured out our moles of acid, then we can find our concentration. So our concentration then, our find concentration of our acid is just moles divided by volume, right? So in this scenario, we have 0.0058175 moles divided by our volume, but remember we want this in liters because our unit has to be moles per liter. Okay, so our volume of acid is 10 mils, which is the same as 0.01 liters. And when we do the math, then we would get 0.58175 moles per liter. So our concentration of nitric acid is 0.582 moles per liter. All right, so that's got the correct number of single digits. I've got my units. There's my final answer. All right, so this is how we can solve this problem. It's just like any other stoichiometry problem that we've done. Let's try another one. So this problem, we've got sulfuric acid is titrated using lithium hydroxide. And they want us to figure out the volume of the sulfuric acid sample that was titrated. So again, like any other problem, when we're dealing with this, we're looking at setting up our balanced chemical equation. So sulfuric acid, H2SO4, plus lithium hydroxide produces water. And the salt in this case would be lithium sulfate, which by solubility rules is soluble. So now looking at this, we need to balance it. I know my lithiums need balancing, so I need a 2 there. And then to balance out the oxygens and the hydrogens, I'm going to need 2 water. So there's my balanced chemical equation. And again, I can write down what I know. I know my concentration of my acid is 0.433 molar. Remember, capital M is a unit, right? Just means moles per liter. Okay, it means the same thing. So capital M as a unit is moles per liter. And we are trying to find the volume of the acid. So that's what we're trying to find. We know the concentration of our base is 1.25 molar, and I know the volume of base used was 15.25 milliliters. So again, I just want to be able to find moles of base, and then using my ratio, I can find moles of acid, right? So this involves the ratio piece. And once we got moles of acid and concentration, we can find volume. So let's give it a try here. So I'm going to convert to moles, or CTM as some people like to talk about it. And I know I've got enough information to find moles of the base, so I'm going to do that first. Moles of base, one is the concentration of the base times the volume of the base, right? So 1.25 moles per liter times our volume, and convert this into liters, right? Because this unit has liter in it, we need our volume to be liters. And so our number of moles of base is going to be 0.0190625 moles. Now, once we've got that, we can do our mole ratio. And our mole ratio is going to then say, okay, our number of moles of acid to number of moles of base. So from our balanced chemical equation, the acid is a 1 and the base is a 2, right? So we can use that ratio and work it out, which essentially means I'm dealing with the number of moles of acid is going to equal whatever the number of moles of base is, so 0.0190625 moles times 1/2. It should be half the amount, right? The acid should have half the amount. So once we figure out that, we're going to get 0.00953.125 moles. And again, I'm not going to round anything until I get to my final answer. But looking at significant digits right now, I'm carrying 3 through here. I should still have 3 significant digits here, right? So just keep track. Sometimes it's good as you're going along to keep track of those things. So my last piece now, I want to find the volume of the acid. So I'm going to put that up here, find the volume of acid. So volume of the acid, right? If we remember our C equals N over V, I'll just write it over here, C equals N over V. We're rearranging, we want V by itself, so the V is going to come up, the C is going to come down, so we're going to get N over C. And we just plug in our moles of acid, which was 0.00953.125 moles. And then we want to divide by the concentration, which was 0.433 moles per liter. And when we're done, we will end up with a volume of 0.022012 liters. So therefore, the volume of acid, L was 22.0 milliliters, right? So if I need 3 significant digits, I'm right to that 0. And all I did was take it from liters to milliliters. So there's my answer, 22.0 milliliters. So that's one scenario where you're dealing with a reaction that had a 1 to 2 ratio. But again, it's any titration problem, it's just stoichiometry. We'll give you one more if you want it. Feel free. If not, turn the video off. Totally up to you. But this one's kind of a neat one. We've got an unknown monoprotic acid. Now, if you haven't heard the term monoprotic before, remember that mono means one, protic means proton, right? So we're dealing with an acid that has one proton in it. So if we don't know what that acid is, we'll put X to represent the anion, and we know it's got to have one hydrogen attached to it because one proton is present. So using this HX in our equation is what we will be using to represent our unknown monoprotic acid. And it was titrated with NaOH. We have 0.5 molar NaOH, and it says if 27.88 mils of base was needed to reach the endpoint of the titration, what was the molar mass of the unknown acid? All right, well, let's take a look, and we'll start this as we would any question. We need a reaction. We need a balanced chemical equation. So we know this is an acid base. We should always get water. And then our salt. Now, our salt involves the sodium from the base and that X piece from our monoprotic acid. So imagine that H gets removed, that proton gets removed. This is going to be an X with a -1 charge. And sodium has a +1 charge, so we only need one of each when we put this together. So this would be our salt that gets created, NaX. Once we've got our equation, we check to see if it's balanced, and yes, it is. Everything here is a 1-to-1 ratio. And I'm just going to write down now what I have. I know my mass is 1.10 grams. They want us to find the molar mass. So if we think about it, molar mass, I'm just going to go up to the side here. Molar mass is mass divided by moles. So we've got a mass. We've got this number we can put in. The other piece we need then are moles. So if I can get the moles of HX, we'll have enough information to find the molar mass. So right now I can't do that, but if I take a look at my NaOH, I know that its concentration of this base is 0.5 molar, and I know the volume of the base, 27.88 milliliters. That's enough information. I can find moles of base. Concentration, volume, find moles, and then use the ratio, right? The ratio will let me get the moles of the acid. So that's our plan. This is our plan of attack here. So the first thing I'm going to do is convert to moles of base. So moles of base should equal the concentration of the base times the volume of the base. So 0.5 moles per liter times 0.02788 liters. Remember to convert that volume to liters. Otherwise, you don't end up with the proper unit for moles. So when we calculate that, we're going to get moles of 0.01394 moles. And then from our moles of base, we want to get to moles of acid. So this is using our ratio. Number of moles of acid to number of moles of base is a 1-to-1 ratio. Therefore, number of moles of acid equals number of moles of base, which is 0.01394 moles. So now you've got moles of our acid, and we've got the mass, right? And now we've got enough information we can find the molar mass. So our molar mass now for this calculation then, so this is our final step, find molar mass. So molar mass is mass divided by moles. We had 1.10 grams of HX and 0.01394 moles of HX. And when we do the math, we get 78.9096 grams, which to significant digits now, we go back. This is 3, so we're carrying 3 through here. This is 3, this is 3. Our answer has to have 3, so it's 78.9 grams per, oh, I messed up my unit, per mole. Whoops. So this should say mole. So then we just write our statement, right? Therefore, the molar mass of HX is 78.9 grams per mole. Right? So there's how we can find a molar mass of some unknown substance and how we might deal with like a solid information as well. So again, titration is the technique that we use to get these specific numbers, but it's the analysis of the titration data is just stoichiometry. Thanks for your time. Have a great day.